September 14th, 2015, 5:51 in the morning, Eastern Time. Two detectors, one in the Louisiana Bayou, one in the high desert of Washington State, simultaneously register a signal. It lasts 0.2 seconds. It's a chirp, a brief rising tone, almost musical, and then gone. What caused it? Two black holes, one 29 times the mass of the Sun, one 36 times the mass of the Sun, merging together 1.3 billion light-years away. The collision was so violent that in the final fraction of a second, it radiated more power in gravitational waves than every star in the observable universe combined, all radiating light simultaneously. Every star, all at once. And it did this silently, invisibly, producing no light whatsoever. We didn't see it. We felt it. A ripple in the fabric of space-time, a gravitational wave, traveled outward from that collision at the speed of light, passed through everything in its path without being absorbed or deflected, crossed 1.3 billion light-years of space, arrived at Earth, passed through the planet, through you, through every atom in your body, and moved two mirrors 4 kilometers apart by 1,000th the diameter of a proton. And we caught it. That's what happened on September 14th, 2015. Before I explain how, or what it means, I want you to sit with the scale of that for just a moment, because the engineering alone is one of the most extraordinary things our species has ever done, and the physics it confirmed had been waiting 100 years for this test. Let's start with what a gravitational wave actually is, because ripple in space-time is the phrase everyone uses, and it's true, and it's almost completely opaque without unpacking it. Einstein's general relativity, his theory of gravity, published in 1915, says something deeply strange. Gravity isn't a force. There's no invisible hand pulling you toward the Earth. What's happening is that mass curves space-time, the four-dimensional fabric that everything exists within, and that curvature is what we experience as gravity. You fall toward Earth not because something is pulling you, but because the shape of space-time near Earth guides you there. Curved space-time tells matter how to move. When massive objects accelerate, they disturb that curvature. Like a moving object disturbs the surface of water, an accelerating mass sends ripples through the geometry of space. Those ripples propagate outward at the speed of light. That's a gravitational wave. Here's what the ripple actually does when it passes through you. It alternately stretches space in one direction and compresses it in the perpendicular direction, like squeezing a rubber sheet from both sides. As the wave passes, distances change, not because objects are moving through space, but because space itself is briefly expanding in one direction and contracting in another. The change is real. The effect on matter is real. It's just almost incomprehensibly small by the time the wave reaches us. The arms of LIGO are 4 kilometers long. The wave from GW150914 changed that length by 10 to the minus 18 meters, 1,000th the diameter of a proton. That's the signal. That's what we had to build an instrument to detect. Einstein predicted this in 1916. He also privately doubted at points that it would ever be detectable. The waves are real, but attenuated by distance, diluted by the vast scale of the universe, they arrive with an amplitude almost incompatible with measurement. Almost. The instrument that caught them works on a principle called laser interferometry. Split a laser beam. Send each half down a perpendicular 4-kilometer arm. Bounce it off a mirror at the end. Bring the two beams back together. If the arms are exactly equal length, the beams cancel each other. Darkness at the detector. If a gravitational wave passes and stretches one arm while compressing the other, even by that subnuclear amount, the beams no longer cancel perfectly. A tiny sliver of light reaches the detector. That's your signal. In principle, this is elegant. In practice, it's the hardest engineering problem anyone has attempted. Every vibration on Earth is louder than the signal. Trucks on a road miles away, ocean waves crashing on coastlines, the thermal jittering of atoms in the mirrors themselves, quantum noise from the photons in the laser. Even light has an uncertainty in its phase that creates noise at the relevant scale. Every single one of these is bigger than the gravitational wave signal you're trying to extract. The solutions are extraordinary. The mirrors are suspended on multi-stage pendulum systems, one pendulum hanging from another, to isolate them from ground vibration. The beam tubes are evacuated to a pressure lower than interstellar space. The mirrors themselves are polished to atomic smoothness and are among the purest objects ever manufactured. The laser power is amplified inside the arms using a technique called Fabry-Perot cavities, bouncing the light back and forth hundreds of times to effectively increase the arm length and reduce quantum noise. And there are two detectors, separated by 3,000 kilometers. LIGO Livingston in Louisiana, LIGO Hanford in Washington. A real gravitational wave, traveling at the speed of light, arrives at both. A local noise source, a truck, an earthquake, a bird landing on the building, that affects only one. If both detectors see the same signal within the light travel time between them, it's a candidate. If it arrives with the right time delay, consistent with a source direction in the sky, it's a detection. This concept existed in the 1970s. The technology didn't. 40 years of physics and engineering brought it to reality, involving over 1,000 scientists across dozens of institutions. The upgrade to advanced LIGO, completed in 2015, improved sensitivity by a factor of 10. The first detection came 16 days after the upgraded detector turned on. 16 days. Now let me tell you what those black holes were actually doing, in physics, not pictures. Two black holes, formed from massive stars in the same stellar system, bound to each other by gravity. They orbit. Slowly, over millions to billions of years, that orbit decays, not because of friction, there's no friction in space, but because the system is radiating gravitational waves, tiny ripples draining the orbital energy. As they lose energy, they spiral inward, closer, faster. The orbit tightens. This is the in-spiral phase. The signal during in-spiral is a slowly rising chirp, frequency and amplitude both climbing as the orbit accelerates. Then the merger. The two event horizons, the boundaries of no return, touch and coalesce. This happens in milliseconds. At that moment, the power output in gravitational waves briefly surpasses the combined luminosity of every electromagnetic source in the observable universe. All of it. Every star, every galaxy, every quasar, all radiating simultaneously. And for that fraction of a second, this one collision outshines all of it in gravitational power. Then the ring down. The newly formed black hole is distorted, wobbling, asymmetric, and it radiates that wobble away in gravitational waves as it settles into a stable spinning shape, like a struck bell ringing down to silence. The whole sequence lasted less than a second in the frequency band LIGO can hear. GW150914, the name given to the event, had a peak frequency of about 150 Hz. If you shift it into audible sound, a brief chirp, rising quickly, then silence. That's it. That's 1.3 billion years of orbital decay and the most energetic collision we've ever detected, compressed into 0.2 seconds of audio. The final black hole, 62 solar masses. The two originals, 29 plus 36 equals 65. 3 solar masses were converted to pure gravitational wave energy, 3 times the mass of the Sun. Gone. Radiated away in the merger. That's 6 times 10 to the 30th kilograms turned into space-time ripples in under a second. On September 14, 2015, when the signal arrived, the detector was in engineering mode, not yet in its official observing run. The scientists who first saw the signal assumed it was an injected test event, a fake signal deliberately inserted to check the analysis pipeline. That was standard practice. They checked the injection log. Nothing had been authorized. Nobody had injected anything. They spent 5 months checking everything, every possible instrumental explanation, every noise source, every potential systematic error. 2 completely independent analysis teams working separately both concluded the same thing. This was real. February 11, 2016, the announcement. The auditorium was packed. The signal was played aloud, that chirp. Kip Thorne, one of the founders of LIGO, who had devoted his career to making this possible, wept. The room, full of physicists who understood exactly what they were hearing, erupted. 100 years after Einstein predicted gravitational waves, 100 years. The Nobel Prize came in 2017. Rainer Weiss, Kip Thorne, Barry Barish, deserved. And GW150914 was not a fluke. It was the opening of a new sense. Since then, LIGO and its partner detector Virgo have catalogued over 90 confirmed gravitational wave events, binary black hole mergers, binary neutron star mergers, neutron star colliding with a black hole. The universe is full of these events. We just couldn't hear them before 2015. GW170817, August 17, 2017. 2 neutron stars merging 130 million light-years away. LIGO and Virgo detected the gravitational waves. 1.7 seconds later, gamma-ray telescopes in space detected a short gamma-ray burst from the same direction. Then optical telescopes found the visible afterglow, then X-rays, then radio waves. The same event observed simultaneously across the entire electromagnetic spectrum and in gravitational waves. Multi-messenger astronomy. For the first time, we watched a cosmic event with completely different physical senses simultaneously. That merger did something else. It confirmed, to extraordinary precision, that gravitational waves travel at the speed of light. The arrival time difference between the gravitational wave signal and the gamma-ray burst was 1.7 seconds across 130 million light-years. The speed difference between gravitational waves and light, less than 1 part in 10 to the 15th power. That single measurement ruled out dozens of alternative gravity theories that had predicted gravitational waves should travel at different speeds. The neutron star merger also produced a kilonova, a flash of heavy element synthesis visible in the optical afterglow. Gold, platinum, uranium, the heavy elements in your jewelry, the ones too heavy to be made in ordinary stellar burning, made in events like this one. We watched it happen. We saw the gold being made. What gravitational waves give us that nothing else can? Light is absorbed by dust, bent by plasma, altered by the medium it passes through. Gravitational waves pass through everything at full strength. They carry information about the source encoded in the waveform itself, the masses of the objects, their spins, their distance, the geometry of the merger, all there if you know how to read it. We tested general relativity in the strong field regime for the first time. Near a merging black hole, space-time curvature is extreme. Nothing in any laboratory comes close. The ring-down signal from GW150914 matches the mathematical prediction of the Kerr metric, the geometry of a spinning black hole, with extraordinary precision. General relativity, confirmed in the most extreme gravitational environment the universe produces, it held. But here's where honesty requires me to say, with all of this confirmed, all of this achieved, there are things we still don't know, things the detections have revealed without resolving. Some of the merging black holes we've detected fall in mass ranges that stellar evolution doesn't easily explain. There are black holes in what's called the mass gap, too massive to form from a single stellar collapse, too light for certain other formation channels. Where did they come from? Sequential mergers? Exotic stellar physics? We don't know yet. Some merging black holes have spins misaligned with their orbital axis. That suggests they didn't form together from stars in the same binary system. They captured each other dynamically in a dense stellar environment. The formation history of these systems is genuinely uncertain. And the deepest gap, general relativity, is a classical theory. It describes gravitational waves beautifully, completely, in the regime we've observed. But space-time, at the Planck scale, must be quantum. In the final instance of merger, in the interior of the black holes involved, we need a quantum theory of gravity, and we don't have one. Every clean detection confirms the classical theory. The quantum layer beneath it remains hidden. Now let me tell you what's coming, because the next chapter is going to be extraordinary. LIGO's current arm length is 4 kilometers. The Einstein telescope, planned for Europe, will have arms 10 kilometers long, underground, triangular. Cosmic Explorer, planned for the US, reaches 40 kilometers. Sensitivity improves by factors of 10 to 100. What currently requires a detection threshold becomes routine catalog data. Mergers we now barely hear will be crisp, detailed, analyzable in ways current signals don't permit. LISA, the Laser Interferometer Space Antenna, changes the scale entirely. 3 spacecraft flying in formation, separated by 2.5 million kilometers. Arm length, not 4 kilometers, 2.5 million kilometers. Sensitive to frequencies no ground-based detector can reach. Supermassive black hole mergers, each component millions to billions of solar masses, will be detectable across the entire observable universe. Compact binary systems will be detected years before they merge, giving us time to point every telescope we have at the source and watch the final plunge in every wavelength simultaneously. And pulsar timing arrays, networks of radio telescopes monitoring millisecond pulsars, have already detected the gravitational wave background, a low-frequency hum filling the galaxy, produced by the slow in-spiral of supermassive black hole pairs across cosmic history. Detected through nanosecond deviations in dead stars' heartbeats. We are building ears for every frequency of the gravitational universe. And the universe, it turns out, is not quiet. It has never been quiet. It has been vibrating, with mergers, with collisions, with the slow death spirals of compact objects, constantly throughout all of cosmic history, at a volume we are only now beginning to measure. For the entirety of human history, we understood the cosmos through one sense: light. Every telescope ever built, every observation ever recorded, every map of the universe, all of it light in some form. The visible, the infrared, the radio, the X-ray, the gamma ray, all electromagnetic radiation, all the same fundamental thing. On September 14th, 2015, at 5:51 in the morning, we grew a new sense. Gravitational waves pass through you right now. Every merger happening anywhere in the observable universe sends ripples through space-time that reach Earth, diminished but real. Before 2015, they passed through you in silence. You had no way to feel them. Now we catch them. Now we decode them. And what we've found is that there's an entire layer of the universe, invisible to light, inaudible before LIGO, constantly active, that has been happening all along. Black holes merging in the dark, neutron stars colliding and forging gold, the slow in-spiral of compact objects across billions of years, whispering in gravitational waves the whole time. The chirp of GW 150914, that 0.2 second signal. It encoded 1.3 billion years of orbital decay, the most energetic event humanity has ever directly detected, 3 solar masses of pure energy, a perfect confirmation of a century-old prediction, all of it arriving at Earth on a Tuesday morning and moving 2 mirrors by 1,000th the width of a proton. We built something sensitive enough to hear that. Einstein predicted the wave in 1916. He doubted at points that we'd ever catch it. He was wrong about that. We caught it. And we're only beginning to understand what the universe has been trying to say.